this lecture, I'm going to talk a little bit about well, external supports. Mostly, what I'm going to talk about here are internal reaction forces. Now, forces. Sadly, one thing I can't do is talk and spell at the same time. Okay. In the last one, we looked at using equilibrium equations to solve for reaction forces. And, you know, in those situations, what we did was looking at what we're going to call external reaction forces. Okay? So, for example, if you have a cantilever beam, there's a tip force, right? At this point, due to the constraint of it being fully supported, there are reaction forces and moments. So when you have a fully supported end, you're going to have a reaction force in both the x and y direction, and also a reaction moment. So what we're going to talk about here is using the same approach, drawing free body diagrams, but how do we determine what are the reaction forces internal in the structure? Now, before I do that, let me just kind of, I think I probably just for completeness sake, I should just go over and categorize the different types of external supports. I don't know, this doesn't really belong in here. Well, it didn't seem important enough to make its own lecture, right? So in this class, we pretty much have the following types of supports going from lesser to greater. So the first type is a free end. This really isn't a support. There's no reaction forces there. The next simplest one is an end or something supported by a roller. In this situation, the body is free to move in the x direction, if you will, but it cannot move in the y direction. Even though the way we kind of draw this cartoon, it looks like it can pull off, you assume it can't pull off. It's fixed completely in the y direction. Probably a better way to draw it would be as follows. And in this situation, what you have is simply a reaction force in the y direction. Next, we can have an end that's pinned. Something like this. So this is fixed both in x and y, but it's free to rotate. So it's free to rotate. So in this situation, this gives us the following types of reaction forces. So this is pinned. This gives us both an x and a y reaction force. No moment. It's pinned. And the last one is fixed. Something like that. Where it can't translate the x or y or rotate. And this one has the reaction force we already talked about. Both an x and a y reaction force and also a moment. Okay? Alright. So last time we kind of used the sum of forces and sum of moments equals 0 to determine these external reaction forces. Well, in this class, one of the things we're concerned about are size and components so that the stresses and the strains do not exceed certain values so we can design these components. The stresses are a result of the internal resultant forces. So if you think of a body, arbitrary body. Possibly this has some distributed loads on it, moments, some point forces, however, and then maybe there's some constraints. Let's fix the side so that there should be some reaction forces satisfying those constraints. Okay, this body's in equilibrium. Every point on this body is in equilibrium. So if we draw a free body diagram of the entire structure, it's in equilibrium. If we draw a free body diagram of any subsection, it's also in equilibrium. Now, what you have to imagine is if I take this potato and I split it into two parts, let's see what we have drawn. Same way. Usually I draw this like flat. Let's imagine it's a flat cut, makes a lot more sense. It's supposed to be the same picture, but kind of split. And there might be, here's those external forces. And now to make it a proper free body diagram, let's not put the constraints, but let's put some reaction forces that correspond to that fixed condition. Okay? Each one of these bodies are in equilibrium. Physically have to be in equilibrium. Now, the way I've drawn those, they're not in equilibrium because I'm missing something. What am I missing here? Well, if we call this body 1 and this body 2, body 2 exerts forces onto 1, body 1 exerts forces onto 2. They both have equal and opposite forces, Newton's third law applying between them. These are the internal reaction forces. Okay? These are the forces that are going to end up giving us stress, which we'll talk about later on. But, that's a quantity of a lot of interest to us. So there's equal and opposite internal reaction forces on this. So the way you have to think of it is there exists some set of forces on body 1 that, if we pull this away, it would exactly equal the forces that body 2 exerts on 1. So if you were a little bug here, okay, and do this thought experiment. The bug sits on the potato. Now we cut the potato instantaneously and apply the appropriate internal reaction forces so that, that 2 would have exerted onto 1, the internal reaction forces. That little bug will see no change, okay? There's no stretching or any change in the deformation of the internal load. It stays exactly the same. Now, I've kind of drawn a continuum here. It was a little difficult to kind of when to turn between continuum and mechanics materials. But in this class, we'll talk about the internal reaction distribution of forces, this traction here. And actually, I have another video that kind of gets into that using some finite element stuff. But what we'll typically deal with in this class is things as follows. Let's see if I can come up with this. Imagine we have the following. So I have a beam that's pinned on one end and on lowers on the other end. And let's put some sort of, and then also there's axial load as well. No, it's not this way. Okay, some force also applied at along the beam axial. Now, inside this beam, all along this length of the beam, we have differing reaction forces. If we were to cut the beam, for example, along this point, somewhere along this point, right, this now splits the beam into two parts, the left and the right part. So I'm going to try and draw the left part. And I'm going to draw not the free body diagram, I'm going to draw the sort of a picture because I have the constraints there. Well, actually, you know what? I'll draw the free body diagram. Okay, so this is a roller, so this actually has a point force acting on it, right? So I'm doing what I told you not to do. I'm kind of being a little sloppy in my free body diagram. But here's the supporting reaction force due to the roller. Okay, and now on the other side, we have, what I have on this side also, the point force. Okay, you also have this point force that's applied on the beam. And then on this side, we have a pin, so we have call this R, B, and FB. So since it's pinned, you have a reaction force both in the X and Y direction. Okay. And this is, these made up against each other. Now, this exerts onto this one, this exerts onto this one. In general, we're going to have three types of reaction forces. You can have normal reaction force in the normal direction. It's like an axial force. That's denoted with N. You can also have a shear force, and we'll talk about this sign difference. We have a shear force, and we can also have a moment. Now, these internal reaction forces and moments are equal and opposite. Right? So, V, as I've drawn here, has the same magnitude as V here, just in the opposite direction. Likewise with M and N. Okay? So, N is the normal force. V is the shear internal reaction force, and M is the internal reaction moment. The book also talks about internal reaction torques. The units of moment and torque are the same, and the way you decide whether something's a torque or a moment, you have to consider the geometry. Technically, they're the same. The units are the same. They're both the moment arm cross with the force vector, but they have a little different connotation. In this sense, we think of this as a bending moment because it actually causes the beam to bend, as opposed to a structure like this, where maybe now this could be a moment as well, applied to this axis, right? But we consider this to be more like a torque because this looks more like a shaft or a torsional element, and this, linguistically we kind of call that a torque. Although from a mechanics standpoint, they really are the same. In fact, I usually stick with moment. Okay, you can think of torque as a subset of moment. Although the book, it makes a distinction between those. All right, so those are the internal reaction forces. That's what keeps the bodies in equilibrium. If you take different cuts, you can draw different free body diagrams and expose different internal reaction forces. So if you need to get the internal reaction forces at this point as opposed to this point, it's going to require two different cuts in the body. Now, this approach of taking the body and cutting it, exposing internal forces, and then using equilibrium equations on the resultant free body diagrams to determine those forces is something we're going to do throughout this entire class. Okay? These forces gives us the stresses, so we have to determine the stresses. First step we'll have to do is the internal reaction force determination. And you'll get so good at this that you'll kind of do it implicitly in one of the steps, but I'm trying to go through a little more rigorously in the beginning here. Okay. So the typical problem you'll see is something like this. Actually, we can almost do the same problem as we did in the last video. Well, let's do this. I will do this beam. Let's do this beam. Let's simplify. So this would be a typical type of problem. Here's a beam. Well, let's fix it on one end. Keep it free on the other end. And then let's have a force. Well, we'll have both a tip force down and then an axial force pressing. Okay? You can think of this actually also as a single force acting along an angle, right? So force. But we broke it into its components. All right. Let's give this thing a length of 24 inches and 2 feet. And let's call this 50 pounds. And this is going to be 100 pounds. Okay? All right. Now, a typical problem would be find internal reaction forces. When you say forces, you also know moments at the midpoint. So, that's the point of interest. It could be any point, all right? So the midpoint in this case is going to be right here. That's 12 inches. Okay? All right. Now, when we look at this, there's a couple of ways you can do this, and I'll go over this slowly. Obviously, we have to take a cut here. Okay. When I take a cut there, that exposes the internal reaction forces at the midpoint. Now, there's actually two free body diagrams that I can use to determine the internal reaction forces. First one, we'll draw the one on the right-hand side. It's actually a little easier to deal with. Here's the one on the right-hand side. Here's the 50 pounds in and 100 pounds down. And then here are the reaction forces. Normal, shear, moment. This distance here is 12 inches, right? Okay. That's one free body diagram. We could also draw the free body diagram on the left side. Now this is a built-in support, so it has a reaction force in the x and y direction as well as the moment. So let's call this point A. So we've got a moment at A, y reaction at A, force in the x direction at A. Called F and R just to keep the subscripts kind of reasonable. Now we also have the internal reaction forces. And okay. Both of these free body diagrams work fine. Okay, you can use either one of these to solve for V, N, and M. They're both fine. Okay. This situation, and the approach is the same way. Okay, you use sum of forces and sum of moments to solve for V, N, and M on each free body diagram. All right. So you want to take care and carefully drawing this. So if we look at the first free body diagram, okay, we can directly write sum of forces in the x, sum of forces in y, and sum of forces around. Well, let's pick this point. Call this point D, right? This point C. Okay. So if we do sum of forces in x direction equal to 0, that gives me minus n minus 50 pounds, 0. We can solve for n. N equals minus pounds. Okay? Now, let me mention something about the direction of the internal reaction forces. Okay? Again, as with the external ones, it's up to you to choose the orientation. And honestly, it doesn't matter again. So people will say, well, when I draw this, well, N has to go in the other direction because the 50-pound force is in. Yeah, that's true, right? And what happens here is we got the negative sign as a result. So that means N actually is 50 pounds going in this way. So it's in compression by 50 pounds. Okay? But it doesn't really matter. For simple problems, you can look at it by inspection. If you're good, maybe more complex problems, you can figure it out by inspection. But as problems get more complicated, especially as you start, it's really difficult to correctly pick the orientation. Now, that being said, why waste your time doing that? So what I recommend doing is not trying to figure out which way the internal reaction forces should go. Just draw them on the free body diagram and then solve for them and be careful about the signs. That's all you need to do. Now, the convention that I use, and we'll talk a little more about this later on when we talk about stresses, the convention I use is if we call this x direction and this y direction, positive x and positive y, this face here has a negative outward facing normal. Okay? The outward normal in this direction is in the minus x direction. So I call that a minus face. And when it's a negative outward normal face, I flip the signs in a sense. So you see the normal points outward positive, right? That's the negative x direction. The V goes in the negative y direction. And the moment is about the negative z direction. So I do all the signs negative. You don't have to do it. You can pick them the other way. You can pick them any way you wish. As long as you're careful with the signs, it doesn't matter. But this is what I do. And actually, it'll make a little more sense with the bookkeeping when we talk about stresses and getting tensile stresses versus compressive stresses. Okay? But, you know, that's the notation I do. Sometimes when I do problems, I'll talk about a positive face and a negative face. Now, in this situation, this is a positive face because the outward normal, that face, that cut face, is in the positive x direction. So you can see the normal vector is in the positive direction, the V is in the positive y, and the moment is in the positive z direction. They are all flipped on this. Now again, you can pick either or. Now, once you assume that n in this free body diagram goes in this direction, well then n in this free body diagram has to go in the other direction. okay? Because these have to be opposite of each other, right? So what I'm saying is, if you want to assume n in this free body diagram is going in, that's fine. But make sure the n on this free body diagram is also going in the direction, or going in the other direction, right? Likewise with n and v. But again, it doesn't matter. Try it yourself. Use the n, flip the direction. You'll get the same thing. You'll get a positive 50, but since n is pointing in this direction, you'll get the same results. All right? Okay. Now we can also do sum of forces in the y equal to 0, and that gives me minus v, it's in the negative direction, minus 100 pounds equals 0. And that gives me, again, v is equal to minus 100 pounds. So actually v on this face is actually going in the other direction, and it's 100 pounds. And the last thing we'll do is sum of moments. Okay? Sum of moments. Let's pick a point. So we'll do sum of moments around point B, and those are equal to 0. So using this free body diagram, you would get sum of moments. Well, we have the moment, the internal moment there. And the way I drew that, that's actually a negative moment. Okay, I drew that so it's going around the negative z-axis. It's a negative face. Okay, so it's a negative moment. The internal reaction shear force B and the internal reaction normal force N, neither of those contribute any moments around B because they go past through that point below 0. Now, this 100-pound force produces a moment in the negative z direction, right? Its moment arm is 12. So that's a negative 100 pounds times its moment arm, which is 12 inches. Okay? And that's it. There's no other moment. This 50-pound force is in line with B, so its moment arm is 0. If it were offset some distance, there would be a moment, but it's not. So the moment arm is 0. So that's all you have. That's equal to 0. So again, this is going to give you the internal reaction moment at point B is going to equal minus 1,200 inches. So that's the solution to the problem. Now, you could have used this free body diagram. There's not a correct free body diagram to use. You can use either or. All right? Some free body diagrams are a little simpler to solve than others, but you can always get the answer. Okay, so let's do the same problem again, but use the second free body diagram, this left side free body diagram. You know, if this were a problem on the exam, at this point you're done. Okay, but I'm just showing an alternate solution. Right? Okay, so now if we look at this, let's make sure it's all on the screen. Actually, just this. Right? Okay. I don't know RA, MA, and F, right? These are the reaction forces due to the support. Okay, but we can determine those. We've done that before. We've done that in statics. We need to look at the free body diagram of the entire structure. So this happens a lot. Sometimes the free body diagram you choose has forces from the external reactions, and those are possibly you don't know those. So you need to draw an additional free body diagram. Of the entire system. It's like an auxiliary. Right? So here's the complete structure. So this is 24 inches to here, 100 pounds down, 50 pounds here, and then we have unknown reaction forces, R, A, F, A, and so they're external, so I drew them all in their positive senses. Positive Y, positive X, and then positive Y, positive Z. All right? And let's do sum of forces about point A equal to 0. So we're going to use equilibrium on a different free body diagram to give us the external reaction forces. And this is fair, okay? Different free body diagram, so equilibrium holds for all free body diagrams in the structure. With the sum of forces in the x, this just gives us Fa minus 50 pounds is equal to 0. Or in other words, Fa is equal to 50 pounds. Sum of forces in the y direction, equal to 0. That gives me Ra minus 100 pounds equals 0. Oops. 0. Ra is equal to 100 pounds. So it's 100 pounds going up. And then we can do sum of moments around A. 0. That gives me A. These guys don't contribute any moment to 0. Neither does the 50, by the same logic as before. But the 100 does give us a moment. It's a negative moment, and its moment arm is 24. So it's minus 24 inches times 100 pounds equals 0. So the external reaction moment, the built-in support, and A, over here, is going to equal 2,400 pounds. Okay? All right. Well, now that we have those, I can then use those on this free body diagram to solve for M, V, and N. All right? So you have to do this additional step because you have to get the external reaction forces that exist in the body. So whenever you have external reaction forces on your free body diagram that you're going to use to compute the internal reaction forces, you might have to use, or you very likely will have to use, an additional free body diagram of the entire system or some other system, subsystem, some other cut, to give you the external reaction forces. Now, practice will let you see, what are judicious free body diagrams to draw that allow you to compute the quantities that you desire, more readily. Just come from practice. Okay, so now we have those. Let's go back and visit this diagram. I know that this is equal to 100 pounds. It's going up. This is equal to 50 pounds, and this is equal to 2,400 pounds. Okay? Now, with that, I can do sum of forces. Now this is using free body diagram 2. This is using FBD 2. All right. Sum of forces in the x direction equals 0. That gives me 50 pounds, right, plus n equals 0. That gives us n is equal to minus 50 pounds, which is exactly what we had before. It means that the n actually has to be pointing in the direction, which you could probably have preferred. Sum of forces in the y direction are equal to 0. So we have 100 pounds up, so it's a positive 100 pounds. And then plus v equals 0. So solving for v, this gives me v is equal to minus 100 pounds. So it's identical to this, same thing. And finally, we can do sum of moments. And let's do sum of moments around point B. You can do it around A. I usually do it around B because it decouples V and N from that. We'll learn from V and N. Okay. So if we're doing moments around point B, we have 2,400 pound inches. That's a positive moment. So 2,400 pound inches. Always put in units. FA produces no moment because it's in line. The moment arm is 0. Right? Perpendicular distance from this point to the line of action of FA is 0. Okay, so that gives you no moment. So 50 pounds times 0. RA, that gives me a moment 100 pounds. This is from RA. Its moment arm is this distance, 12 inches. Okay. And now what else we have? V, that has no moment arm with respect to V. Goes through it. Likewise N. And now we just have M, which is a positive moment. Okay, so plus M equals 0. Now solving for M, we get that M equals 1,200 pound inches. That's for this term, minus 2,400 pound inches. That's this term, and that's equal to minus 1,200 pound inches. Okay? So again, same exact value. Right? So it doesn't matter which free body diagram you use. Okay? Sometimes you might have to use multiple free body diagrams. As you get good at these and practice, you know your homework, you'll find it easier to choose which ones work better. Usually, it's a good idea to try and pick a free body diagram that uses less reaction forces from constraints. Right? Now, you might not always be able to do that, and if that's the situation, you might have to use an additional free body diagram to determine the external reaction forces, okay? So if you want to go through sort of steps of doing this, first is identify where you're going to cut the structure to expose those internal reaction forces. Okay, this is going to expose internal reaction forces. Okay, so in this particular case, you can see cut right through the middle because that's where the problem asks you to find the internal reaction forces. Once you do that, we're going to have to draw the free body diagram. Now this is going to be the cut body, right? And with exposed internal reaction forces. Obviously, this torques as well. Now, this one's kind of optional. Maybe it's 2B. This is optional. You won't always have to do this, is maybe a better way to say it. You may need to use additional free body diagram to determine some of the external reaction forces. Okay? You might not have to do that. So like in this particular case, if you chose the right free body diagram, you really never have to determine external reaction forces. When you begin, you maybe not so savvy, you might choose the left one. That'll still work, but you will need to use an additional free body diagram to get the internal reaction forces that I have. Sometimes you'll have no choice, okay? And the final step, well, in this case, we're using the same thing. Use sum of forces equal to 0 and sum of moments equilibrium equations to obtain external reaction forces or, if if you don't have to do this, final step is to use equilibrium equations on the original free body diagram from step 2 to determine the internal reaction forces. Right. And for this class, for me, since I'm the instructor, I need you to be very careful about clearly labeling the orientation and the sign. Okay? So, for example, if you draw your free body diagram, if you use, which group rules? Here it is. Okay. If you use, you're talking about this free body diagram, and you call n equal to 50, it's incorrect, because n equal to 50 means that n is going in this direction. It's not, it's going in the opposite direction. Okay? So don't drop the sign, or if you're going to do it, report it like follows. This would work. It's, okay? That would be an appropriate answer. Okay? So you can see I've given all the correct orientations and values. Okay? This would also work here, but make sure you don't drop the signs. Right? If you mix them, you know, you might not get. I have to kind of guess that you know what you're talking about. Okay. Okay. So wait. So these are the steps for when you get these problems. We have to determine the internal reaction forces. Okay. That's what you do. Don't forget. Sometimes you might have to use multiple free body diagrams to determine some other forces, so that you get all the forces known for your free body diagram that expose A. Okay? And again, we're going to use these in subsequent chapters to compute stresses. Right? That's what we're going to use to size or to design components of the flow. All right?